exciting! Let Paimon see! The natural position, which is the positional propensity of an entity in natural motion, in contrast with an object in forced motion. When free from external influences, every entity displays the tendency to follow its natural trajectory.
So, you got that?
What the heck was this guy reading? Hello, Count Sacke here, back with another Genshin Impact video. Today, I have a little fun puzzle I wanted to tackle. I'm going to explain what Alhaitham was reading. The Traveler and Paimon certainly didn't understand it, but hopefully by the end of this video, you will. I have a lot of other math, physics, and engineering videos on this channel, so be sure to have a look around if you find that interesting. If you like what I have to offer, be sure to like and subscribe. You can also support me via channel memberships, where you can get special perks like gaining access to members-only videos, and with super thanks, where your comments will be highlighted and stand out among the rest. Lastly, I would like to thank everyone who participated in my previous video topic poll, allowing for this video to become reality. With that, let's get started. Before we can even jump into any sort of physics, we need to first figure out what the heck is even being said. To make sense of this, I'll split it into two parts. Let's start with the first part. The natural position, which is the positional propensity of an entity in natural motion, and I'll cut it off here. Notice the comma after natural position. This indicates that it is simply declaring what the natural position is. The thing that makes it hard to understand is the jargon, positional propensity.
Like seriously, who even says that?
So, what do positional and propensity mean? According to Google, the IRL Akasha, positional means relating to or determined by position. And propensity is an inclination or natural tendency to behave in a particular way. Putting things together, this statement seems to be saying that the natural position is the position an entity in natural motion tends to move toward. Let's continue analyzing the remaining quote. In contrast to an object in forced motion, when free from external influences, every entity displays the tendency to follow its natural trajectory. Let's focus on the second and third phrases. All that is being said is that entities follow their natural trajectory when there isn't anything influencing them. For the first phrase, it just says that an entity in forced motion doesn't follow whatever the natural trajectory is. As to what the external influences and natural trajectory are, I'll get into that later. What we've unpacked so far makes sense, but there seems to be something wrong or incomplete with what Paimon read because, well, it kind of feels like the first and second parts are unrelated. Take for example this sentence, Nahida, the Dendro Archon, saved Sumeru. What I can do is shorten it to just Nahida saved Sumeru. Regardless if I get rid of that middle part, it still makes sense because I can connect the first part to the second part, Nahida saves Sumeru. With whatever Paimon read, however, I can't figure out what the first part connects to. Because of this, I can only suggest that Paimon didn't finish reading the entire thing, so we have nothing to connect the phrase with. If we just focus on the second part, specifically, when free from external influences, every entity displays the tendency to follow its natural trajectory. It sounds kind of familiar, especially to those who have taken a physics class before. People, including myself, immediately thought of Newton's first law of motion. However, I also think it could potentially be two other things. Something from Einstein's general relativity,
Yes, the Einstein.
and something called the principle of least action, which is one of the closest things we have to a theory of everything. But you might be asking, how do these things even relate to whatever the heck Alhaitham was reading? Well, sit back and relax, you're in for a ride. Let's start off with Newton's first law. Newton's first law says that when the sum of all forces acting on an object is zero, the momentum of that object remains the same. However, what is momentum and what is a force? To understand these concepts, I believe the best approach is to start from zero and build up the concepts. Let's start with a question. How can we quantify motion? There are a lot of things we can use, but a natural first guess is speed. However, speed is just a number, or more technically, it's a scalar. Scalars are just a number, they don't have any sort of direction associated with them. This would be like trying to drive a motorcycle, but your eyes were just purely focused on the speedometer instead of the road. Not very useful and very dangerous. Maybe instead we have something that incorporates both speed and its direction. The closest thing that matches this is something called velocity, which does have both speed and a direction. This is because velocity is something called a vector quantity. If you want to know more about vectors, I talk about them in more depth in my video, How to Measure Distances in Genshin Impact. So, if you're interested, feel free to check it out after this video. So velocity seems like it solves all our problems because it has both speed and a direction. You know where you're going and how fast you're going. Seems like everything you would need for motion, right? Well, there's something very subtle that might catch you off guard. If velocity alone is used to quantify motion, this means that two completely different objects moving at the same speed and direction are equivalent. Does that sound right? Let's consider an example to check this logic. A rock and a cotton ball of the same size are thrown at you with the same speed. If motion is just the velocity, the rock and the cotton ball have completely equivalent motion. Don't you think it kind of feels a little bit off? If I hit you with a rock, that's certainly more painful than getting hit with a cotton ball, so I think it's quite natural to suggest that the rock has more motion. The next question to do is to ask, why do we think the rock has more motion compared to the cotton ball? Well, when you think about it, the rock was initially traveling towards you, but then once it hits you, don't you think it's odd that the rock suddenly changes direction? And speed, too. The speed is also different. Maybe what's actually happening here is that motion is being transferred to you, and you feel that transfer of motion as pain. The idea that the rock has more motion than the cotton ball is actually more in line with the transfer or change of motion. It feels more painful because the rock is able to transfer more motion to us. But of course, this begs another question. What exactly is causing the rock to have more motion? Well, a lot of smart people did a bunch of experiments showing that the total mass times velocity before and after transferring motion remains the same. Because the quantity, mass times velocity, is conserved, it was given a special name, momentum. Vector p equals m times vector v. In this equation, vector p is the linear momentum, m is the mass, and v is the velocity. This means that we can simply write the sum of momentum at 1 is equal to the sum of momentum at 2. This is known as the law of conservation of momentum. Because momentum seems to be special and aligns with our understanding of motion, we say that momentum is defined as the state of motion. With our rock and cotton ball example, the reason why the rock felt like it had more motion is because it had more mass than a cotton ball. Let's explore some implications of the law of conservation of momentum. Say we have an object with mass m, moving with velocity v at one instance in time. If we were to leave the object, then check back on it sometime later, what would we expect, assuming nothing happens to the object while we were gone? We can say that the initial momentum is p1 equals m times v. But we also know that momentum is conserved, so the later momentum p2 must be equal to p1. This implies that p2 is also equal to mass times velocity. The object still has the same mass, and it's still moving in the same direction with the same speed. This should make sense. I mean, nothing ever happens to the object, so there isn't really a reason for the object to suddenly change direction or suddenly change speed or even its mass. It just follows common sense, really. Conservation of momentum works quite well for a lot of scenarios involving collisions and objects that bounce off of things. However, there's yet another subtle thing about momentum that we need to consider. Here's a simple example. Let's say there's a box on top of ice, and you give the box one big shove. Based on the law of conservation of momentum, the box should just slide forever. But jumping back to reality, you'll notice that the box actually slows down, and eventually even stops moving altogether. Where did the momentum go? Wasn't momentum supposed to be conserved? You gave the box some momentum when you pushed it, but why did it stop? The answer to that question is forces. A force is an interaction on an object that attempts to change its momentum over time. Or in other words, a force attempts to change an object's state of motion. Mathematically, we say the sum of all forces acting on the body is equal to the derivative of momentum with respect to time. The symbol in front of the F is called sigma, and it represents a sum, so therefore it means that you have to add up all the forces acting on the object, and this d divided by dt term is the derivative with respect to time. Be a little bit careful though. While it looks like a fraction, it's technically an operator. This is in the same light that plus is the addition of two things. You don't take plus and divide it by plus. That doesn't make any sense. So yeah, it's a similar vein to that. In any case, d dt signifies the rate of change in a quantity over time. This means that you can read this equation as the sum of all forces equals the rate of change in momentum over time. If you were paying close attention, I didn't say forces change an object's momentum. I said that forces attempt to change an object's momentum. The reason why I say attempt is because it's possible for the forces to completely counteract each other, resulting in no change of motion. This is exactly Newton's first law. When the sum of all forces acting on an object is zero, the momentum of the object remains constant. This does not necessarily mean that the object is not moving. Zero change in momentum does not mean zero velocity. An object can be moving with constant velocity, and its momentum will remain the same if the mass remains constant as well. It's also important to remember that velocity and momentum are vectors, meaning they have both direction and magnitude, as I've repeated many times. The direction is where the object is going, and the magnitude is how fast the object is moving, or at least a measure of how fast it is. So, if an object is moving with constant speed in a circle, that object doesn't have a constant momentum because its direction is changing. If you consider an object with constant mass, constant momentum implies that the object doesn't accelerate, meaning that its velocity doesn't change. A constant velocity then means that the object will move in a completely straight line. To prove this, I'll have to get into some calculus. Unfortunately, I still have yet to find a good way to explain calculus on a beginner-friendly level, so I apologize if you don't really understand what's happening. Let's assume that we have an object of constant mass m, constant velocity vector v, and the initial position at time equals 0 to be vector x0. What we want to do is to figure out what its final position should be after t amount of seconds, or any unit of time. In our case, we know that the sum of all forces acting on the object is 0, therefore the momentum is constant over time. Mathematically, this is represented by the fact that the derivative of momentum with respect to time is 0. However, we know that the mass of the object is constant as we assumed earlier, so we can factor it out from the derivative and divide out the mass. When we take the integral with respect to time, we see that the velocity doesn't change over time either. Good to know the math matches our understanding, and our assumptions too. To calculate position, know that the velocity is the derivative of position with respect to time. After taking the integral with respect to time on both sides and substituting all the boundary conditions, this results in the equation of motion for an object with constant velocity. Vector x is the object's position at time t, vector v is the velocity, and vector x0 is the initial position. If you compare this with the equation of a straight line, y equals mx plus b, you should be able to see the connections. Y is x, m is v, x is t, and b is x0. If there is ever a point where a net force acts on the object, then this equation may not necessarily hold true anymore because the directions and everything might change. Something I want to point out is that there are actually two different types of motion, translational and rotational motion. This implies that there are two types of momentum. Momentum for translational motion is just the linear momentum, p equals mv. And for rotational motion, it has angular momentum, L equals I omega. Likewise, there is something called a quote-unquote rotational force, but it is called a force moment, or simply moment, which attempts to change an object's angular momentum. And here's the equivalent of Newton's second law for rotations. Going back to the original topic, what exactly is the external influence and natural trajectory in the case of Newtonian mechanics? From this point of view, the external influences are specifically forces and moments. When they don't cancel out to zero, they change an object's linear and/or angular momentum. This implies that the natural trajectory is whatever path an object with constant momentum travels. In the case of a non-rotating object with constant mass, its natural trajectory will simply be a straight line pointing in the direction of the object's velocity, where its position can be calculated with this equation. Newton's first law is a pretty big contender for what Alhaitham was reading. After all, the terminology seems to match up quite well. So, what other physics could he have possibly been reading? Einstein's theory of general relativity is the currently accepted and well-proven theory of gravity. One interesting thing about his theory is that he came up with a thought experiment called the equivalence principle. This says that over relatively small distances, gravity is indistinguishable from an acceleration in the opposite direction. It sounds kind of weird, but it's a matter of perspective. From your point of view, you technically don't move, and the world is the one that's shifting around you. Anyway, if we can't distinguish between the ground accelerating upward relative to you, can you really say that gravity is a force? In Einstein's eyes, no. Gravity is not a force. However, if gravity isn't a force, then what's causing you to accelerate towards the ground? The answer is not a force, but the curvature of four-dimensional space-time, and these are the Einstein field equations. These describe the relationship between space-time curvature embodied through the stuff on the left and energy on the right. G mu nu is the Einstein tensor, lambda is the cosmological constant, G mu nu is the metric tensor, T mu nu is the stress energy momentum tensor, G is the gravitational constant, and C is the speed of light in a vacuum. In short, energy and mass distort the geometry of space and time, causing it to curve. This looks like one equation, but there are actually 10 second-order nonlinear partial differential equations, where the goal is to solve for the metric tensor. There are technically 16 equations, but due to the tensors being symmetric, it actually reduces to 10. Actually, solving the Einstein field equations is very difficult and involves a lot of tensor calculus and physics I barely understand, so I can't really go into much details. Typically, to solve the equations, people use simulations and numerical approximations rather than exact equations. So, once you solve the Einstein field equations to get the metric tensor, you can now describe the motion of objects through this four-dimensional spacetime in the absence of forces. The motion is calculated with the Geodesic Equation, which is shown on screen. The acceleration of the object is the d squared x mu d tau squared term, while the curvature is embodied in the gamma mu alpha beta term, also known as the Christoffel symbol. Once again, actually solving this requires a lot of tensor calculus, so giving any more details is outside my realm of knowledge. To follow a geodesic, all forces must be absent. However, general relativity doesn't consider gravity as a force, as I mentioned earlier. In the geodesic equation, if you multiply mass to the whole thing, you're suddenly dealing with forces. M times the second time derivative of x, mu, is just mass times acceleration, which we know is a force. The second term with the Christoffel symbol is analogous to an inertial force like the centrifugal and Coriolis force. It's not exactly a one-to-one analogy though, because inertial forces are still forces and have counterparts. For the centrifugal force, its counterpart is the centripetal force. With gravity in general relativity, there is no force counterpart to it. There is only curvature, so yeah. If you want to learn more about inertial forces, I highly recommend this video by OV Astronomy, The Reality of Fictitious Forces. It's a really good video, and it also doesn't shy away from hiding some details. Anyway, with both the Einstein field equations and the geodesic equation, general relativity can fully explain how an object can accelerate towards the ground without any forces acting on it. When there isn't a net force acting on an object, it will just follow the curvature of spacetime. This path is what is predicted by the geodesic equation, and it's called a geodesic. What general relativity is saying is that when you're on the ground, you have a net force acting on you, even if it doesn't seem like it. That force is the normal force, which is exactly what prevents you from falling through the ground. While you're on the ground, you're not following a geodesic. In fact, the ground is blocking you from following it. It is only when you are in free fall that you are following a geodesic, because gravity is not a force. So if Alhaitham's book is talking about general relativity, the external influences also refers to forces, just like in Newton's first law. It's just that in Einstein's point of view, gravity isn't included as one. The natural trajectory then refers to a geodesic because in such a case, there are no forces acting on you. There is only spacetime curvature. Pretty complicated, huh? Funnily enough, the math was also very difficult for Einstein himself. Anyway, with two contenders for what Alhaitham was reading, let's learn about the last one, the principle of least action. If there was one encompassing equation that almost all of physics was connected to, it is this. Delta S is equal to 0. This says that the variation of the action is 0. The variable s is called the action, and the delta is called the variation operator. In calculus, if you set the derivative of a function to 0, you can determine the maximum or minimum points of the function. Likewise, this variation of the action being set to 0 finds the minimum or maximum of the action. This is also why the principle of least action is also more accurately referred to as the principle of stationary action, because it doesn't necessarily have to be a minimum, it can be a maximum action. So, what the heck is action? Well, S is equal to the integral of L with respect to time from t0 to t1, where L is the Lagrangian, which is the kinetic energy minus the potential energy. Long story short, kinetic energy is the energy due to motion, and potential energy is the energy due to location.
You got that?
Sure, we have equations for the action and the Lagrangian, but what are they conceptually and physically? Unfortunately, if you look around on the internet, you won't really find many interpretations of these quantities, and usually people only talk about how they miraculously spit out equations of motion and how they're 100% superior to Newtonian mechanics in forces in every way possible.
Sorry, I have a little bit of a gripe against that. But anyway.
Knowing how something is used doesn't necessarily explain what it is, though. And plus, this is physics, so it needs to have some sort of physical explanation, otherwise it doesn't really tie back to reality. One common thing I notice people ask is this: why is it that kinetic energy minus potential energy is the one that's minimized or maximized, and not kinetic energy plus potential energy? Surely, the total energy of the system would make more sense, right? Veritasium himself actually expresses his confusion about this in his video about the topic. It turns out that this minus sign is the very clue that might help us understand the Lagrangian, action, and the principle of stationary action. In my Engineering of the Flamestrider video, I talked about the first law of thermodynamics. If you want to learn more about energy, you should go and check it out after this one. Anyway, in short, the first law of thermodynamics is an equation that expresses how energy transfer can affect a system. The equation is the following: delta Q minus delta W plus dEm equals dE system. dE system is the energy of the entire system, which is just the sum of its internal kinetic and potential energy, which are U, Ke, and Pe respectively. We'll assume that heat transfer, energy transfer via mass transfer, and the change in internal energy are zero. This results in an equation that shows the relationship between work, kinetic, and potential energy. When dealing with calculations and equations, we oftentimes have to be careful with how we interpret positive and negatives. The same goes for the first law of thermodynamics. When an object's kinetic energy or potential energy increases, it has a positive value. However, when they decrease, they are negative. If we have an overall increase in the kinetic energy and decrease in the potential energy, we determine the work to be the following: negative delta W is equal to dKe increasing minus dPe decreasing. However, we can also consider a case where the kinetic energy decreases and the potential energy increases. We can ignore the negative sign in front of the work, it's simply another sign convention. The important thing is to recognize that these terms look like the Lagrangian, and so I think it's pretty safe to say that the Lagrangian is the measure of the amount of work done. It is as simple as that. The reason why there's a negative sign between them is simply because of sign conventions. We're considering one of them to be decreasing and the other one to be increasing, so one of them has to be negative and the other has to be positive. Now that we understand that the Lagrangian is simply a measure of the amount of work done, we should be able to understand action. From its equation, it is the integral of the Lagrangian over time. This therefore implies that action also measures work, but it also considers how long or the duration in which the work was being done. There's one thing I would like to point out though. Work is not the only way to affect a system, as there are many other different types of energy transfer. So instead of just saying work, we can actually just talk about energy transfer in general. So, therefore, we can say that action is a measure of how much energy conversion and energy transfer takes place over a period of time. With our understanding of action, we can now figure out what the principle of least action says. The principle of least action says that the path an object takes is one that minimizes or maximizes energy conversion and energy transfer. If that still doesn't make sense to you, here's the too long didn't watch. The universe is lazy.
Even physics is calling us out.
I would like to note that this is just my personal interpretation. I could be wrong, so any physics experts out there can feel free to correct me in the comments. So we have at least some sort of conceptual understanding now, but what is it actually for? The principle of least action is used to derive equations of motion. So if we solve this equation, delta S is equal to 0, we'll be able to determine how an object moves. Notice that the action is a definite integral, meaning it has both an upper and lower bound, t1 and t0 respectively. You essentially start off knowing the initial and final position of the object, however, we don't know how it moves between the points. There are many different ways that an object could get from point 1 to point 2. The principle of least action says that the path which has the minimum or maximum action is the one an object takes between these 2 points. Here's the thing, we don't actually always start from delta S equals to 0, it would be very tedious to do any computations with it. In fact, we use a different equation that is derived from it called the Euler-Lagrange equations. I'll show you how it's done. Unfortunately, understanding what I'll be doing requires even more calculus knowledge, so I apologize again in advance. Alright, let's go ahead and solve this thing. In concept, we imagine that there is a path that is able to minimize the action, then for every point along that path, we slightly change it or vary it. This operation of variation is indicated by the delta symbol. However, there are 2 positions which cannot be varied, the endpoints. Why we can't vary those positions, I hope is obvious. It's like this. You take a picture of an object, then take another picture sometime later. You can determine where they are in the pictures, and it will forever be in that position in those pictures. This means that delta Qi evaluated at t0 and t1 equals 0. Next, we have to recognize that the Lagrangian is a function of position and velocity, where q is the position and q dot is the velocity, which are also functions of time themselves. This should make sense, as L is equal to Ke minus Pe, where kinetic energy is related to motion and potential energy is related to position. Because of this relationship, we get this. The variation of L is equal to the partial derivative of L with respect to Qi times the variation of Qi plus the partial derivative of L with respect to Q dot I times the variation of Q dot I, and all of that is integrated over time. If you've ever taken a calculus course, this should look very similar to the total derivative or total differential of L. Something that would be useful is if we could factor out delta Qi. It's just that it helps simplify things. However, one of the terms is delta Qi dot. We somehow need to get rid of the time derivative, and what we can do is use integration by parts. The integration by parts formula is shown on screen, and if we cleverly choose u to be the partial derivative with respect to q dot of L, and we let dv equal to the variation of q dot dt, things turn out very nicely for us. We can see here in this first term, partial L partial Q dot I times the variation of Qi, it is evaluated from t0 to t1. However, we stated earlier that the variation at t0 and t1 must be 0, so therefore this first term cancels out to 0 as well. And then we're essentially left with the negative integral from t0 to t1 times the time derivative of partial L partial q dot I times the variation of q times dt. Substituting this into the equation from earlier, we can now factor out delta qi. So where do we go from here? Well, this integral needs to evaluate to 0. However, delta qi is not generally 0, except at the endpoints. This implies that the integrand itself must be equal to 0 to satisfy this condition. And at last, we arrive at the Euler-Lagrange equations. The partial derivative of the Lagrangian with respect to the position minus the time derivative of the partial derivative of the Lagrangian with respect to the velocity equals 0. If we calculate the Lagrangian and substitute it into this equation, it'll spit out an equation of motion. Let's consider a simple example: a ball rolling forward. We can say that the position q must be x and the velocity q dot must be v. The equation for translational kinetic energy is 1/2 mv squared. As for the potential energy, we'll assume it's just 0. This gives that L is equal to the kinetic energy mv squared divided by 2. After substituting that into the Euler-Lagrange equations and going through all the calculus, we see that we get the law of conservation of momentum. The time derivative of momentum is 0, and if we assume that the ball has a constant mass, this will result in the equation we derived earlier. What was this video about again? Oh right, the thing Alhaitham was reading! So, what would be the natural trajectory considering the principle of least action? For me, I interpret the natural trajectory to be the path that is predicted by the Euler-Lagrange equations. But what about the external influences? There doesn't seem to be anything that could relate to it. Do you remember how when I used the first law of thermodynamics, I ignored heat transfer, mass transfer, and changes in the internal energy? Those are the missing links. Energy transfer in general doesn't always involve work, and it doesn't necessarily always affect kinetic and potential energy. For example, it could go to the internal energy, or the energy could end up being rejected as heat. To be more precise, the Euler-Lagrange equations are no longer valid when non-conservative forces are at play. Or rather more accurately, you have to modify them just slightly. This raises a question: what exactly is a non-conservative force? To answer that, a simpler question to ask and to answer is, what is a conservative force? The classification of conservative and non-conservative forces is based around work. To make this short, work is simply defined as force times displacement. If you apply a force and the object moves, work is done on that object by the force. It's important to note that you need both movement and the force. You can apply a force, but if no movement occurs, no work is done. That's just how the definition works. So, a conservative force is a type of force that when applied to an object, the amount of work done doesn't depend on the path it travels. So let's say I have two endpoints, A and B. If a conservative force was applied to an object bringing it from A to B, the amount of work for any path would be the same. I could literally travel all across Teyvat and back, and the total work would still be the same going in a straight line. In short, conservative forces do work independent of the path. They only care about the initial and final position. Non-conservative forces are just the opposite. The work they do depends on the path. Mathematically, we say this. The integral over a closed loop of a conservative force is equal to 0, or alternatively, the curl of a conservative force is equal to 0. If this integral isn't 0, then you're dealing with a non-conservative force. Some examples of this include friction, pushing or pulling a box, and air resistance. To be able to account for these non-conservative forces in the principle of least action, we add an extra work term. This term embodies the work done by non-conservative forces. If you go through all the variational calculus again starting from the principle of least action, you'll get this slightly different form which just has a sum of non-conservative forces on the right. Just to clarify, the conservative forces are already baked into the Lagrangian through its potential energy. With that, we can finally say that the external influences in the context of what Alhaitham was reading are the non-conservative forces as they change the path of an object only under conservative forces would have traveled in the first place.
You got that?
Let's recap our three contenders. Alhaitham could be reading Newton's first law, general relativity's geodesics, or the principle of least action's Euler-Lagrange equation. For Newton's first law, the natural trajectory is all the positions an object with constant momentum will traverse. In Einstein's general relativity, it's a geodesic. Lastly, for the principle of least action, the natural trajectory is the path of least action which is predicted by the Euler-Lagrange equations. Something interesting about all these different branches of physics is that the external influences always seem to be a force of some kind. A net force on an object will prevent it from following its natural trajectory. In Einstein's theory, the same is true, but gravity is not considered as a force. Lastly, for the Euler-Lagrange equations, only non-conservative forces are considered as external influences. With all that said, what is the most likely thing Alhaitham was reading? Go ahead and comment the one you think is most likely and why. I'll wait. Alright, in my opinion, I think that the most likely topic is... none of them. Wait, what? What do you mean none of them? I only presented 3 options. Alright. I was being dishonest by presenting a false trichotomy. If we really do look at what he was reading, the physics sounds very primitive and more focused on technical jargon rather than being able to make actual predictions. The wording of the book sounds a lot more like how ancient Greek philosophers tried to explain motion, like Aristotle's physics or Aristotelian physics. On this great video by The History of Physics titled The History of Physics Season 1 Episode 6, Aristotelian Physics, he says this.
Aristotle agreed with his predecessors that there are 4 elements, earth, water, air, and fire. But he expanded on this. Each one has its natural resting place, and if allowed to move naturally, they will each move toward their natural resting place in a straight line.
Isn't that amazing? The phrasing and wording matches perfectly with whatever Alhaitham was reading. The terms such as natural resting place feel similar to the term natural position, and move naturally is synonymous with natural motion. There's also this segment from the video.
This takes care of natural motion, but clearly things also move when we push or pull them. You could call it unnatural motion or forced motion.
Again, the terminology matches perfectly. What? Why are you looking at me like that? Are you bothered by the fact I spent all this time talking about 3 different branches of physics only to pop up with this other solution I didn't foreshadow from the beginning? Alright, I'll be more fair to you guys. If I had to choose among the original 3 I proposed, I would choose Newton's first law. While it's unclear how much physics knowledge Teyvat has, I believe they're unlikely to have come to the point of general relativity. Or actually, maybe they have already cracked general relativity because they have this thing. But either way, based on the brief description of what Paimon read, there actually isn't much of an indication that curvature is involved. For the concept of the principle of least action, it's too based in mathematical rigor to be properly described by what he read. Even if the wording and phrasing is primitive, Fontaine's level of technology suggests that they should at least be able to perform force and moment analysis to have created such complex engineering designs. Now, I'm still actually cheating here a bit because Newton's first law, the Geodesic Equation, and the Euler-Lagrange equation are technically viewpoints about the same thing. This is evident because their external influences are all forces, just different classifications. All equations suggest that forces, or at least some types of forces, must be absent for the object to maintain its current trajectory. However, I'm still cheating here. You see, the principle of least action can actually be used to derive Newton's second law and the geodesic equation. So essentially, these are all almost the same concepts, just very different levels of complexity, hence why they all feel so similar and why I simultaneously thought of these three different physics concepts when reading that line. In conclusion, I explained how Newton's first law, Einstein's general relativity, and the principle of least action can all be related to what Alhaitham was reading. However, it is most likely he was reading something similar to Aristotelian physics. The reality is that whatever Paimon read isn't actually that confusing. It's the word positional propensity that throws everything off. Basically, it sounds like someone was just trying to sound smart rather than actually communicating the idea effectively. I hope I actually did communicate what I was trying to teach here effectively, though. If you're wondering why I bothered to explain all these different physics, even though Alhaitham was probably reading Aristotelian physics, it's because I wanted an excuse to talk about these topics, and I find them interesting. Sorry for putting you through all that, but hopefully I gave you a taste to the depth that physics can reach. I didn't even look at quantum mechanics, because I don't understand it. Anyway, if you enjoyed the video, be sure to like and subscribe. You can also support me with super thanks and by becoming a channel member. If you could, sharing the video just really helps me out a lot. I do personally really doubt that many people will watch this. It was a really brief resting moment from all the amazingness that was the Sumeru Archon quest, and well, yeah, just in general, this topic doesn't seem to be something that someone would casually just look for. So yeah. I would also like to take this time to apologize to my viewers as this video took a very long time to come out. I gave a few updates every now and then, but I was very busy over the past few months. And again, yeah, I know this will very much hurt my channel. I don't expect a lot of people to watch this at all in the slightest, especially considering how long it's taken for me to make this video. But yeah, anyway, I hope the wait was worth it. Thanks for watching and hope you've enjoyed. But there's something that's still bugging me. Just one unanswered question I cannot grasp. Why is a linguistics major reading a physics book?